Hello and welcome to the Deep Learning lecture series. This is fifth lecture related to the vanishing backward propagation. In last lecture, we understood the concept of learning rate and gradient descent. In case of neural network which predicts using forward propagation, we assume that the network is having optimized weights and biases. But the question is how to train the neural networks and optimize the weights and biases for given data set. Actually, training is done in supervised learning mode. In this case, each data point has associated weights and biases. When the output is not obtained as per the predicted value, it is essential to train the weights and biases for the input data points. Now, question is how to train it. We have actual value which we call ground truth value t and the predicted value. The difference between the difference we obtain between ground truth value t and the predicted value is error e. This we refer as e. It represents cost or loss function. So the concept here is to propagate the error back to the network one step backward and use it to perform gradient descent on the weights and biases in the network. We take an example of a simple network which contain only two neurons, one as input and another as output. The input is x1 for the first neuron having weight w1 and bias b1. Similarly, for second neuron, the input is a1, weight is w2 and bias is b2, which produce output a2. We calculate square errors between the ground truth, which we refer as t, and the predicted value as a2. The square error represents cost or loss function. In reality, we don't train the network having single data point. There exist thousands of data points in actual neural networks. Hence, the error can be computed as mean square error. So, the first step is to calculate the error, which is MSE or mean square error. Now, we want to use the error E to update W2, B2, W1 and B1 by propagation in backward manner. To update the W2 using the error E, however, the error E is not a function of W2. It is a function of A2. So, we will apply the backward chain rule. If you can see that here, we will obtain derivation of E with respect to A2, then derivation of A2 with respect to Z2 and derivation of Z2 with respect to W2. This is how we will obtain the derivation of E with respect to W2. Z1 is function of X1, A1 is function of Z1 and Z2 is function of A1. And finally, A2 is function of Z2. The error is average of some square of ground truth T and output A2. Hence, it's a difference among ground truth T and output A2 and it's a square error. It's a square of that, some square of that. Hence, to update the weight W2, we obtain the derivation of E with respect to weight W2. It is chain product of derivation E with respect to A2, then derivation of A2 with respect to Z2 and derivation and again Z2 with respect to W2. We obtain derivation of E with respect to A2 here. Then we obtain derivation of A2 with respect to Z2. As such, A2 is sigmoid function. So you can see the result over here. We obtain derivation of Z2 with respect to A2, which is product input activation A1 and weight W1 and addition of bias B1. And finally, using this chain products, we obtain the derivation of E with respect to W2. Similarly, we will obtain the derivation of E with respect to bias B2 as chain product of derivation of E with respect to A2, derivation of A2 with respect to Z2, and derivation of Z2 with respect to B2. By simplifying this, we will obtain derivation of E with respect to bias B2. Similarly, we will go ahead further in back propagation and obtain derivation of W1 and B1 similarly. So, you can see that derivation of error which is with respect to W1 can be obtained as dot products of derivation of E which is function of A2, derivation of A2 which is function of Z2, derivation of Z2 which is function of A1, derivation of A1 which is function of Z1, and derivation of Z1 which is function of W1. By simplifying this, we obtain derivation of error E with respect to weight W1 of first node, and similarly derivation of E with respect to bias B1 of first node. Hence, we can update the W2 now. Similarly, we will update W1 as well. And as we saw the previous slide, we will apply same approach to update our bias B1 as well. So we understood how back propagation works and how we upgrade weights and bias. Let us understand back propagation with one example now. It will give you clear idea how the back propagation actually works. Let us take an example which we took in case of forward propagation. The example used two-layer network each having one node. As you see, the input x1 is 0.1 and weight w1 and bias b1 for the first node are 0.15 and 0.40 respectively. This value we have taken for example. We calculate z1 as x1.w1 plus b1 and then activation function a1 as by applying sigmoid function on z1. We obtain value of Z1 as 0.415 as a result and value of A1 as 0.6023. Now, we will obtain computation value Z2 for second node where the input value is activation value A1 which is 0.623. Weight and bias are 0.45 and 0.65 respectively. Using these, we obtain value of Z2 as 0.9210 and now the activation function A2 will be sigmoid of Z2 which we get as 0.7153. Hence, 0.7153 is predicted value for the input x1 equal to 0.1. So, using the forward propagation, we obtain value of Z1, A1, Z2 and A2 for input x1 equal to 0.10 for this example. As we see, the predicted value obtained is 0.7153. Let us assume that for example, our actual value which we also call as ground truth value T is 0.25. So, using the ground truth value T and actual value which we obtained for A2 as 0.7153, we can find the error which is difference among them. So, error E is mean square of A2 and T which is 0.1083. Now, using backward propagation, we will update the weights and biases for fixed iterations which is also called epochs. These predefined iteration may be 1000 or some fixed numbers. Other way is we perform the iteration until we achieve the error below some threshold value. For example, 0.001. So we keep on performing the same action, having a forward propagation, again go back and perform the backward propagation, improve the weight and biases, and again go ahead in the same way. For this example, we consider the threshold value equal to 0.001 and learning rate eta equal to 0.4. We have already derived the equation to update the W2, B2, W1 and B1 in previous slides. Let us just keep our obtained values Z2, A2, Z1 and A1 in those equations to obtain the updated weights and biases. First we update W2 and for that we find the gradient and multiply with the learning rate n equal to 0.4 and then deduct it from W2. This is how we obtain updated W2. As you see, W2 is obtained as 0.427 and similarly we obtain B2 as B2 equal to 0.612. In similar way, we will find updated values for W1 and B1 as well. The gradient value obtained for the W1 is 0.001021 and the updated value for W1 and B1 will be 0.1496 and 0.3959 respectively. This is our first iteration. Now, this is a result of first iteration after performing first forward propagation and then calculating the gradient descent, applying it on back propagation and obtaining the values. After completion of our first iteration, we obtain updated W1, B1, W2 and B2. Using these values, we will again perform forward propagation and find Z1, A1 and then Z2, A2. Again, after achieving the predicted value as A2, we calculate the error and again perform the back propagation in process to update W2, B2, W1 and B1. We will perform this forward and backward propagation for either fixed iteration or epochs times or until we achieve the threshold error value between ground truth T and predicted value A2. In this example, we consider it as 0.001. Let us summarize our action. Step 1 is initialize weights and biases for the network. Step 2, we repeat the following steps. First is calculate network output using forward propagation. Then B, calculate error between ground truth P and predicted value. Then C, perform back propagation and update weights and biases. And D, repeat from step A until predetermined iteration steps or the error between ground truth and predicted value reach to particular threshold. Hope you understand the concept of back propagation. This lecture covers the concept of back propagation in detail using mathematical explanation. In actual coding, we don't use these steps for each nodes. We have very rich inbuilt functions in TensorFlow and Keras library. So, we conclude this lecture here. We learned about mathematics behind backpropagation and understood one example. In coming lecture, we will understand about problem related to backpropagation and how to overcome it. This problem is called Vanishing gradient descent problem. We will also understand different activation functions and which one is better to choose out of them. With this note, I sign off. Learn, share and grow. Have a great day. Thank you very much.